This is EE300 Fall 2016, Module 3, Video 3, Impulses and the Impulse Response. We want to review what we've done previously. We want to look at what happens when you excite a circuit with a very short waveform and maintain the area of the waveform constant. Then we want to define what the unit impulse is, the delta of t function, and then we want to summarize what we've done here to look at the future. So to review, we previously introduced network functions, also called systems functions sometimes. We had two different flavors of that. One was the driving point impedance or admittance. Those are just the inverse of each other, arithmetic inverse. And that's the ratio. The impedance is the ratio of the voltage in the S domain to the current in the S domain. The admittance is the ratio of the current to the voltage. So those two are arithmetic inverses of each other. We also had the idea of a transfer function. We looked at voltage to voltage transfer functions, but they can actually come in any of the combinations. So you can have a current input and a voltage output, or a voltage input and a current output, and we call all of those a transfer function. If they're in the same variable, it's going to be a dimensionless function, but if there's a input is a current and the output is voltage, you're going to have units of ohms, and if the input is voltage and the output is current, you're going to have units of 1 over ohms. So here's an example. Here's the classic parallel RLC circuit with a current source input. We'll first find the driving point impedance. These are parallel elements, so that makes it easy to find the admittance. So to find the impedance, we'll find the admittance first. So the admittance of an element is just 1 over its impedance, and then admittances in parallel add. So 1 over R plus SC plus 1 over SL. SC is 1 over SC, right? That's the admittance of the capacitor. So then to find the impedance, we just invert all that. So we have 1 over that expression. We want to clear out to get a trailing term of 1 first, so we get multiplied through by SL over SL. And then we want to get a leading term of 1, so when we do partial fractions, we'll be able to do that. And so we divide everything through by LC over LC, and we end up with the driving point impedance being 1 over C times S over S squared plus S times 1 over RC plus 1 over LC. We'll talk about what these things mean in the near future. What does it mean to have a 0 at S here? How does that relate to the circuit elements? And then how do the poles we know already relate to the natural response of the circuit, and what it would like to do if it's just left to relax. To find the transfer function between the current through the inductor and the drive current here, again, it's a parallel circuit, and to do a current divider, so it's the admittance, 1 over SL of the inductor over the sum of the admittances times the input current. Again, we do the same kind of algebra to clear things out, and we get that the transfer function between the input current and the output current is 1 over LC over S squared plus S plus S over RC plus 1 over LC. We saw that we could find the differential equation from the transfer function or the network function. So the differential equation at the input, which is not the same as the differential equation at the output, but we take the network function and we cross multiply. So we get S squared, we get the denominator times V1 on the left, and we get the numerator times I1 on the right, and then we identify multiplying by S as differentiating. So multiplying by S twice would be differentiating twice. We can do the same thing on the transfer function. We cross multiply to get second derivative of I2 plus 1 over RC, first derivative of I2 plus 1 over LC times I2 equals 1 over LC times I1. You can see that you need to develop the technique of reading off the differential equation from the transfer function without formally going through the cross multiplication. But it works because of the cross multiplication. We can use this to find the output of a circuit. So here's the same circuit with some simple parameters, 1 ohm resistor, 1 Henry inductor, and a half a farad capacitor. And let's find the unit step response. So we put in a step of current starting at t equals 0 of 1 amp and hold it there forever. So we again sort of cross multiply. V1 of S is going to be the driving point impedance times I1 of S. We plug in the parameter values. The 1 over c is turned into 2's, and everything else is 1's. So that's easy. So we get 2s over s squared plus 2s plus 2. And then multiply that by the transform of the input, which is 1 over s. In this case, the s's cancel out. The s in the numerator of the transfer function, or the driving point impedance, and the s in the input Laplace transform cancel out. And so here we're doing 2 over s plus 1 quantity squared plus 1, which we recognize as the Laplace transform of e to the minus t times sine t with an amplitude of 2. And that's in volts. And here's a graph of the output. It's got a little bit of oscillation in it, but it dies away fairly quickly relative to the rate of oscillation. This is sine t has a period of 1 over 2 pi, so it's fairly slow. And then the exponential is going at a rate of 1 per, decaying 1 exponential per unit time. So this thing doesn't have much chance to oscillate before it decays away. We can do the same thing at the output. Again, we've got the transfer function. We plug in our parameter values. It looks a lot like it. There's no s there. We put in the 1 over s, and now we have to do partial fractions. I did the partial fractions on another sheet of paper someplace. So here's the values we get. 1 over s. The coefficient of the pole at minus 1 plus j is minus 1 plus j over 2, and the coefficient of the pole at minus 1 minus j is going to be the conjugate of that. So we get an e to the minus t from the pole, the real part of the pole at minus 1, and then we're going to have oscillations at a rate t, cosine of t and sine of t, and the amplitude of the cosine is twice the real part of the residue, so that's minus 2, and the amplitude of the sine is minus twice the real part of the minus twice the imaginary part of the residue of the pole with the positive imaginary part. So here we get the 1 minus e to the minus t for both of them, and then it's cos t plus sine t inside the parens with a minus sign on the outside. Again, it's a unit step input, so that's a zero state response input. So we get a u of t in the output. We had that in the previous slide too. I just didn't make a point out of it. And this amplitude is in amps. And here we can see that we get a constant output after time. We have the transient response, the e to the minus t cos with the oscillations in it, and that goes away. And eventually we're left with a constant 1 amp for the steady state. So let's look at what happens if you put short waveforms into circuits. We're going to look at 3 different waveforms: a rectangular pulse, a triangular pulse, and what we call exponential pulse. The first 2, of course, have finite. They cut off completely. Here's a rectangular pulse. And we rigged things up here so that the pulse has an amplitude that's the inverse of its width. So the product of the amplitude and the width is always 1. So this is a unit pulse. We're calling it delta sub 1. And the definition then is that it's 1 over delta in the region 0 to delta, and it's 0 everywhere else. And we can write that using the unit step function. So we have a unit step function minus a unit step function of the same amplitude, and those will cancel each other out for t greater than delta. We can find the Laplace transform just by using the definition of the Laplace transform of the constant, and then the delay theorem or delay property. So we get the amplitude 1 over delta over s, and then we get 1 minus e to the minus s times delta. That's the delay term. So what happens if we put this into our good old RC circuit? So we know the transfer function of the RC circuit is 1 over RC over S plus 1 over RC. We've done that already. If you're not comfortable with that, then 1 over SC over R plus 1 over SC, and then do the algebra to get the transfer function. And then we multiply that by the Laplace transform of our input, which is this 1 over delta all over S, all times 1 minus e to the minus s delta. And then we leave this term with the deltas, the 1 minus e to the minus s delta on its own for a while, and we do the partial fractions on the terms just involving s plus 1 over rc and s. So we get 1 over delta over s, 1 over delta over s plus 1 over rc, a minus sign there. And we recognize that as the usual step response of the RC circuit because we built this waveform out of a step, and then we'd had a delayed step. And so because we're in a zero state response world now, we have some nice things that happen, like superposition happens. So we have the response to the unit step, and we have the response to the delayed unit step. And so once we found this response, we just say, oh, the e to the minus s delta just delays that whole thing. And so we get this a copy of it, but delayed by delta and doesn't turn on until delta. And we can take that apart piecewise. We know that before t equals 0, everything's 0. Between 0 and delta, we just get that first term because the second term is still 0. And then after the second term turns on at delta, we can say, oh, this is going to the 1 over delta and the minus 1 over delta are going to cancel out. And we can factor out an e to the minus t over rc, and we're left with this e to the delta over rc minus 1 term. So we see it's going to grow, and then it's going to decay away. And it's going to start decaying away at when the step we had turned off. I'm sorry, that picture's not there right now, but you have to keep it in your mind. So we input this waveform, and let's say what happens is to this expression down here for t greater than or equal to delta as delta gets small. Well, we're going to use a Maclaurin series to approximate e to the delta over e to the x, basically. And you know that e to the x can be approximated by 1 plus x squared over 2 plus x cubed over 6 plus, up to how many factors you want to go, x to the n over n factorial. So we only need a few terms here. So we just take look, we've got an e to the delta over rc. We've got a 1 here. We'd like to get rid of the 1. That's what we're trying to do, and yet keep something to tell us what's going on here. So 1 is probably not a good approximation, but 1 plus delta over rc is a good approximation. Delta's small. The 1's go away. The delta over rc, the delta kills off the delta over there, and we get 1 over rc e to the minus t over rc. So it's just a decaying exponential. We put in a very short pulse, and the wave voltage across capacitor just decays like an exponential. What happens when we put in the short pulse, but it's triangular shaped? So again, to keep the area at area 1, we have an amplitude of 2 over delta, and then a width delta. And again, as we know, delta smaller, it's going to get taller and it's going to get narrower. We can do some algebraic formulas for this. So this is 2 over delta. The slope of this line is minus 2 over delta square. So we have minus 2 over delta square t. Between 0 and delta, we can write that in terms of the unit step function. There's a constant 2 over delta. There's a negative ramp with an amplitude 2 over delta square times t. And then to make this thing turn off, we have to start adding in a positive ramp with amplitude 2 over delta square at delta. And so that's how we've superposed these three waveforms to build this finite duration, these three infinite duration waveforms to build this finite duration waveform. We take the Laplace transform of each of the terms. The third term is the delay of the second term, so we expect to get this 1 minus delay factor, and we do. And so we have the 2 over delta as the amplitude of the 1 over s, and we have the 2 over delta squared as the amplitude of the 1 over s squared, and we have the delay factor. I write up the algebra on a separate sheet. It's really a bit of a bear, and there's a good amount of bookkeeping, and I don't expect you to work through this. And even here, just to look at the raw response from each of the terms. You have the response to the unit step, and you can see the 1 minus e to the minus t over rc that you ought to be fairly familiar with as a step response of an RC circuit. Then you have the response to the ramp. And the response to the ramp is going to be a ramp because just like the response to the constant is a constant less the e to the minus t over rc, the response to the ramp is a ramp less the e to the minus t over rc. There's actually a 1 minus e to the minus t over rc because you have to include 1 over s squared and 1 over s and 1 over s plus 1 over rc. So again, you work through all the math. That's just the response to the ramp itself, and then you get the response to the delayed ramp, which looks just like the response to the ramp itself, except it's delayed. It's ugly. There's no denying that it's ugly, and you're not used to having to go through all the details, but you can start to see what might happen here. You've got some t, 2t over delta square. You've got 2t over delta square. They've got opposite signs. They're probably going to cancel out. These terms are probably going to cancel out. There's a lot of stuff that's going to go away once you start looking at this thing piecewise. What happens at t equals 0? What happens, and particularly what happens when delta is small and you look for t greater than delta. So when you look for t greater than delta, all those terms cancel out, and you end up with 2 over delta squared over rc, e to the minus t over rc, and then this e to the minus delta over rc, minus 1 minus delta over rc. Well, last time we approximated our exponential as for small delta as 1 plus delta over RC, and that would kill off everything. And we're looking for something interesting, so we go to the third term of the Maclaurin series, and we add in the 1/2 delta over RC squared. And when we do that, the 1 plus delta over RC and the minus kills off the -1 minus delta over RC. And we have this nice, the 1/2 kills off the 2, the delta kills off, the delta square kills off the delta square, and the RC squared kills off one of the RCs here, and we're left with one of the RCs here kills off the RC there. We're left with 1 over RC e to the minus t over RC, which happens to be the very same thing we got out for the initial square pulse. So you put in a square pulse, you put in a triangular pulse, as long as they're short relative to the time constant of the circuit, you get the same thing out. Let's beat this horse to death. Here's an exponential pulse. I'm sorry, the scales didn't come up here. It's got an amplitude of 1 over delta. It's got a time constant of delta, so it has a unit area. And so here's the pulse decaying away as the input. The Laplace transform of that, is 1 over delta, s plus 1 over delta. We put that into our circuit, and again, work through all the various Laplace, do the inverse Laplace transforms, and you get this 1 over RC minus delta, e to the minus t over RC, the exponential associated with the natural response, and then the e to the minus t over delta, the exponential associated with the input. It starts at t equals 0 at t equals 0, like a zero state response should be. And then as delta gets small, we're going to factor out the e to the minus t over RC. We're left with this term over here. We have this t here in this one, unlike the previous cases where we just had a delay term. So we look at this and say, oh, 1 over delta is a lot bigger than 1 over RC. So we can approximate this whole thing as e to the minus t over delta. And then you realize as delta is getting smaller, that's a 1 minus e to the minus t over time constant waveform. And the time constant is getting shorter and shorter, so it's looking more and more step-like. The exponential goes way faster, basically. And so as delta gets small, you can ignore this term and just treat it as a constant 1. And so you get 1 over RC e to the minus t over RC u of t, and that's the same thing we got in other cases. So something seems to be going on that says no matter what you do, as long as the input waveform is sufficiently short, and we scaled things such that they all have the same area, an area of 1, you get the same thing out. And these should be V3 of t or something else. I mean, it's V2 of t for the delta 3 input. That's right. So this concept that as long as the pulse duration is short relative to the time constant of interest, the duration of things you're interested in the world, any sufficiently short waveform with the unit area has the same response. For that circuit, it was 1 over RC, e to the minus t over RC u of t, but it works for anything. And part of the reason it works for anything is because for all three of those waveforms, as long as you let your delta go small, if you went back to the Laplace transforms of those, and I'm sorry I don't have it on the slide, but there's just restrictions on time. So go back and look at the Laplace transforms of those 3 short pulses, and you see that in the limit as delta goes to 0, they all go to 1. So whatever this thing is, and we're going to call it a unit impulse, and we're going to denote it by delta of t, its Laplace transform is 1. So if we put that into a waveform as the input to a signal, a system, a circuit, we're going to call the output the unit impulse response. And since the output in the Laplace domain is the transfer function times the input in the Laplace domain, and the Laplace transform of the delta function is 1, then the impulse response is the inverse Laplace transform of the network function. And so it's often denoted h of t. The impulse response is denoted h of t, since the network function is denoted h of s. It's drawn as an arrow, and it's got a unit. You denote the area of the impulse by a number in parentheses beside it. So here's our unit impulse 1. It's got a Laplace transform that is 1. It's 0 everywhere except at t equals 0, and it's got to be very large there, as we've seen from the 3 examples we used previously. And it has the property that it has a unit area. You integrate over all time, and you get 1 back. So all of that area is concentrated at t equals 0. This thing's called a generalized function. You can't assign a value. The 1 is not the value of the impulse. 1 is the area of the impulse over all time. It's very tall there, but as we have mentioned before, you can't assign infinity as the value of a function in the non-infinite domain. So we can't say delta of 0 equals infinity. It breaks the rules of mathematics. So we can't assign a value to this function, so it's not a nice function. It's a mean, ugly, nasty function. It's not something you assign values to, but it has good properties. And that is, when you multiply it by a continuous function and take the integral, it picks out the value of that function at t equals 0. And those properties together are the true defining relationship of the impulse. It's 0 everywhere except at t equals 0, and it's very large there. It has a unit area over all times, and it's if the function is continuous at t equals 0, and my integral got lost here. So you have integral minus infinity to infinity f of t delta of t dt equals f of 0, this expression we had back here. You can show this thing's an even function. We're not going to try to do that here. But that means that we have to include just a little bit on just a smidge, just a nudge, a tad, just to the left of t equals 0, so that we incorporate the entire function under our Laplace transform. So we redefine our Laplace transform to start at 0 minus, not just at t equals 0. And now we can put our delta of t in there, and since it picks out the value of the function at t equals 0, we can get 1 back for the Laplace transform of the delta function. This is going to change what f of 0 means in terms of the differentiation theorem, and what f of 0 means in terms of the initial value property. So you're going to look at those on the homework. So let's find the impulse response of the RLC circuit we looked at earlier. So it's just the inverse transform of the network function. So for the driving point impedance, if we put a unit current, impulse of current in, then we just take 1 times the impedance, the driving point impedance there, and inverse transform that, plugging in the parameter values, the component values we had previously. We get 2s over s squared plus 2s plus 2. This is buggy. That's not right. This would need to be an s plus 1 for that to be true. So need to s plus 1 and a minus 1. So this is buggy here. So I'm going to have to work this out, and I'll give you the corrected version later. I apologize for that. The network function, the transfer function, we're okay on that one. We have the network function is 2 over s squared plus 2s plus 2. Multiply by 1, we get 2 e to the minus t times sine t u of t. That is, on this case, since there's no s, there's no problem. We just have the beta over s plus 1 quantity squared plus 1 quantity squared. So we just get an amplitude 2 here. Over here, we've got the 2s, but we actually need we need an s plus 1 to go with the e to the minus t in the numerator. And so we need to add a 1 and subtract a 1. We actually add a 2 and subtract a 2, so we can factor out the 2 and get s plus 1. And so it's probably going to have something to do with equal amplitude cosines and sines. But again, I'm going to have to work that out separately for you. Apologies for that. So in summary, we introduced the unit impulse function. We found that the Laplace transform of the unit impulse function is 1. So if we apply unit impulse as the input to a circuit, we just take the inverse transform of the network function to get that response. And we call that thing the impulse response, and we denote it by h of t, and it's widely used. And we'll talk about how that relates to the, start talking next week about step response, and the week after that about sinusoidal steady state response. And they're connected to the impulse response, but we're not going to explore too much of that in this class. That's more of the topic for signals and systems, where you introduce convolution and sort of finding the output of the response directly in the time domain. We're going to continue working in the Laplace frequency domain for the rest of the term here, and not go down the convolution path. So those of you who've seen convolution before can breathe easy. We're not going to do the convolution path in this term. This has been Module 3, Video 3 of E300 Fall 2016.